Introduction to sets. In this video, we are going to see about introduction to sets. A finite set can be described, at least in principle, by listing its elements. The formula A is equal to 1, 2, 4, 8 says that A is a set whose elements are 1, 2, 4 and 8. For infinite sets and even for finite sets, if they have more than just a few elements, ellipses are sometimes used to describe how the elements might be listed. B is equal to 0, 3, 6, 9 goes on. C is equal to 13, 14, 15 up to 71. The sets B and C could be described this way. B is equal to x. X is a non-negative integer multiple of 3. C is equal to x. X is an integer and 13 lesser than or equal to x lesser than or equal to 71. The expression before the vertical bar represents an arbitrary element of the set, and the statement after the vertical bar contains the conditions or restrictions that the expression must satisfy in order for it to represent a legal element of the set. For any set A, the statement that x is an element of A is written x is an element of A and x is not an element of A means x is not an element of A. We write A subset equal to B to mean A is a subset of B, or that every element of A is an element of B. A subset equal to B means that A is not subset of B. There is at least one element of A that is not an element of B. Finally, the empty set, the set with no elements, is denoted by empty set. Functions definition. In this video, we are going to see about functions definition. If A and B are two sets that is possibly equal of function f, and A to B is a rule that assigns to each element x of A an element f of x of B. We write f A provides B to mean that f is the function from A to B. Example, the function g 2 power n provides 2 power n defined by the formula g of A is equal to AU of 0. A function f from A to B we call A the domain of f and B the codomain of f. The domain of a function f is a set of values x from which f of x is defined. We will say that two functions f and g are the same if and only if they have the same domain. They have the same codomain and f of x is equal to g of x for every x in the domain. If f is a function from A to B, a third set involved in the description of f is its range, which is the set that is a subset of the codomain B. F of x, x element of A. The range of f is a set of elements of the codomain that are actually assigned by f to elements of the domain. Logical statements and its laws. In this video, we are going to see about logical statements and its laws. Logic involves propositions which have truth values, either the value true or the value false. The propositions 0 is equal to 1 and peanut butter is a source of protein have truth values false and true, respectively. A proposition involving a variable, that is, a free variable terminology we will explain shortly, may be true or false depending on the value of the variable. If the domain or set of possible values is taken to be n, the set of non-negative integers, the proposition x minus 1 is prime, is true for the value x is equal to 8 and false when x is equal to 10. Compound propositions are constructed from simpler ones using logical connectives. We will use 5 connectives which are shown in the table below. In each case, P and Q are assumed to be propositions. Connective, symbol, typical use, English translation. Conjunction, P conjunction Q, P and Q. Disjunction, P disjunction Q, P or Q. Negation, negation P, not P. Conditional, P conditional Q, if P then Q, P only if Q. Biconditional, P biconditional Q, P if and only if Q. For the other 4, easiest way to present this information is to draw a truth table showing the 4 possible combinations of truth values for P and Q. Proofs and basic proof techniques. In this video, we are going to see about proofs and basic proof techniques. A typical step in a proof is to derive a statement from initial assumptions and hypotheses or from statements that have been derived previously or from other generally accepted facts using principles of logical reasoning. The more formal the proof, the stricter the criteria regarding what facts are generally accepted, what principles of reasoning are allowed, and how carefully they are elaborated. A few basic proof techniques in the simple proofs that follow. Example: the product of 2 odd integers is odd. To prove for every 2 integers a and b, if a and b are odd, then ab is odd. Proof: the conditional statement can be restated as follows. If there exist integers I and j so that a is equal to 2i plus 1 and b is equal to 2j plus 1, then there exists an integer k so that ab is equal to 2k plus 1 or proof will be constructive. Not only will we show that there exists such an integer k, but we will demonstrate how to construct it, assuming that a is equal to 2i plus 1 and b is equal to 2j plus 1. We have ab is equal to 2i plus 1 into 2j plus 1 is equal to 4ij plus 2i plus 2j plus 1 is equal to 2 into 2ij plus I plus j plus 1. Therefore, if we let k is equal to 2ij plus I plus j, we have the result. We want ab is equal to 2k plus 1. An important point about this proof or any proof of a statement that begins for every is that a proof by example is not sufficient. An example can constitute a proof of a statement that begins that exists, and an example can disprove a statement beginning for every by serving as a counterexample, but the proof above makes no assumptions about A and B except that each is an odd integer. Relations and equivalence relations. In this video, we are going to see about relations and equivalence relations. A function f from a set A to a set B as establishing a relationship between elements of A and elements of B. Every element x element of A is related to exactly one element y element of B, namely y is equal to f of x. A relation R from A to B may be more general in that an element X, element of A, may be related to no elements of B, to one element or to more than one. We will use the notation ARB to mean that A is related to B with respect to the relation R. Definition: a relation from A to B and a relation on A. For two sets A and B, a relation from A to B is a subset of A into B. A relation on the set A is a relation from A to A or a subset of A into A. The statement A is related to B with respect to R can be expressed by either of the formulas ARB and AB, element of R. As we have already pointed out, a function f from A to B is simply a relation having the property that for every x element of A, there is exactly one y element of B with x, y element of f. In this special case, a third way to write x is related to y with respect to f is the most common, y is equal to f of x. In the example above statement, Sally has lived in Atlanta seems easier to understand than the statement Sally, Atlanta, element of R, but this is just a question of notation. Definition of equivalence relations. A relation R on a set A is an equivalence relation if it satisfies these three properties. R is reflexive for every x element of A, x R x. R is symmetric for every x and every y in A. If x are y, then y are x. R is transitive for every x, every y and every z in A. If x are y and y are z, then x are z. If R is an equivalence relation on A, we often say x is equivalent to y instead of x is related to y. Languages and its examples. In this video, we are going to see about languages and its examples. A language to be any set of string over an alphabet of symbols. An alphabet is a finite set of symbols such as A, B or 0, 1 or A, B, C up to Z. We will usually use the Greek letter 2 to denote the alphabet. A string over 2 is a finite sequence of symbols in 2. For a string x, modulus of x stands for the length, that is, the number of symbols of x. In addition, for a string x over 2 and an element sigma, element of 2, n sigma of x is equal to the number of occurrences of the symbol sigma in the string X. The null string A is a string over 2, no matter what the alphabet 2 is. By definition, modulus of A is equal to 0. The set of all strings over 2 will be written 2 asterisk. For the alphabet A, B, we have A, B to the power of asterisk is equal to A, B, AA, AB, BA, BB, AAA, AAB, goes on. A language over 2 is a subset of 2 to the power of asterisk. Here are a few examples of languages over A, B. The empty language. A, AAB, another finite language. The language pal of palindromes over A, B, that is strings such as ABA or BAAB that are unchanged when the order of the symbols is reversed. X element of A, B to the power of asterisk, NA of X greater than NB of X. X element of A, B to the power of asterisk, modulus of X greater than or equal to 2, and X begins and ends with B. The language of legal Java identifiers. The language expression of legal algebraic expressions involving the identifier A, the binary operations plus and asterisk and parenthesis. Some of the strings in the language are A plus A into A and A plus A into A plus A. The language balanced of balanced strings of parentheses, that is, strings containing the occurrences of parentheses in some legal algebraic expression. Some elements are A. The language of numeric literals in Java, such as -41, 0.03 and 5.0e-3. The language of legal Java programs. Here, the alphabet would include upper and lowercase alphabetic symbols, numerical digits, blank spaces, and punctuation and other special symbols. Statement and proof of mathematical induction. In this video, we are going to see about statement and proof of mathematical induction. Mathematical induction is a mathematical proof technique most commonly used to establish a given statement for all natural numbers, although it can be used to prove statements about any well-ordered set. It is a form of direct proof and it is done in 2 steps. The first step, known as the base case, is to prove the given statement for the first natural number. The second step, known as the inductive step, is to prove that the given statement for any one natural number implies the given statement for the next natural number. From these 2 steps, mathematical induction is the rule from which we infer that the given statement is established for all natural numbers. Strong principle and its proof. In this video, we are going to see about strong principle and its proof. We present another proof by mathematical induction to show that every positive integer 2 or larger can be factored into prime factors. To prove for every natural number n greater than or equal to 2, n is either a prime or a product of two or more primes. For reasons that will be clear very soon, we modify the statement to be proved in a way that makes it seem like a stronger statement. To prove for every natural number n greater than or equal to 2, every natural number m satisfying 2 lesser than or equal to m lesser than or equal to n is either a prime or a product of two or more primes. A basis step. When n is equal to 2, the modified statement is that every number m satisfying 2 lesser than or equal to m lesser than or equal to 2 is either a prime or a product of two or more primes. Of course, the only such number m is 2, and the statement is true because 2 is prime. Induction hypothesis. K greater than or equal to 2, and for every m satisfying 2 lesser than or equal to m lesser than or equal to k, m is either a prime or a product of primes. Statement to be proved in the induction step. For every m satisfying 2 lesser than or equal to m lesser than or equal to k plus 1, m is either prime or a product of primes. Proof of induction step. For every m with 2 lesser than or equal to m lesser than or equal to k, we already have the conclusion we want from the induction hypothesis. The only additional statement we need to prove is that k plus 1 is either prime or a product of primes. If k plus 1 are prime, then the statement we want is true. Otherwise, by the definition of a prime, k plus 1 is equal to *r s for some positive integers r and s, neither of which is 1 or k plus 1. It follows that 2 lesser than or equal to r lesser than or equal to k and 2 lesser than or equal to s lesser than or equal to k, and so the induction hypothesis implies that each of the two is either prime or a product of primes. We may conclude that the product k plus 1 are the product of two or more primes. Recursive definitions with example. In this video, we are going to see about recursive definitions with example. Recursion is a technique that is often useful in writing computer programs. In this section, we will consider recursion as a tool for defining sets. Primarily, set of numbers, sets of strings, sets of sets, that is, of numbers of strings. A recursive definition of a set begins with a basis statement that specifies one or more elements in the set. The recursive part of the definition involves one or more operations that can be applied to elements already known to be in the set, so as to produce new elements of the set. As a way of defining a set, this approach has a number of potential advantages. Often, it allows very concise definitions. Because of the algorithmic nature of a typical recursive definition, one can often see more easily how or why a particular object is an element of the set being defined. It provides a natural way of defining functions on the set as well as a natural way of proving that some condition or property is satisfied by every element of the set. Example: a factorial can be defined recursively. A factorial of x is equal to x into factorial of x minus 1 for x greater than 1 is equal to 1, for x is equal to 1 or x is equal to 0. The base criteria for the function is that x is equal to 1 or x is equal to 0. That is, the function does not call itself when it reaches x is equal to 1 or x is equal to 0. The function calls itself whenever x is not 1 or 0 and moves closer to the base criteria as x is reduced at every recursive call.